Okay, so back in the section on parameterization, um, we didn't introduce it then, just basically saved it for now, just trying to pick some battles for then and some for now. But if you have a two-dimensional parametric curve given by the x-coordinates given by f of t and the y-coordinate by g of t, and t goes from, well, a starting number to an ending number, and let's just say we don't have those constants here yet, so they're called alpha and beta. Then so this is a curve, right? A bug is traveling along a certain path, and you'd like the length of that curve. It is an integral from alpha to beta of root the derivative of x squared, and then plus the derivative of y squared. So why does it look like this? We won't go through deriving this in detail, but I guess I'll just say that what's happening here is this does look a lot like the Pythagorean theorem, yeah? In that you have something squared plus something squared, and then that result is being square rooted. Well, that change in x with respect to time and the change in y with respect to time, those really form the legs of a right triangle. And so you square those, and then you take, you add, and then you take the square root. And this really ends up being what's going on. What is this integral? If you were to set up the Riemann sum, you're really just adding up a bunch of tiny little hypotenuses. That's the idea behind what's going on. Don't worry about that detail too much. If you were curious why the formula looks the way it does, that's a brief explanation. But the point is, this ends up giving you the length of that parametric curve. Or in other words, if a bug starts at time alpha and ends at time beta and travels according to this parameterization f of t, g of t, then you could imagine this length, it's like the odometer reading on that bug. And then there's a 3D version which doesn't look all that different or all that surprising. You just have to tack in a dz over dt squared as another summand inside the radical. But the point is, if these are the formulas for the lengths of parametric curves in 2D and in 3D, then the same, at least in principle, vector functions you could think of as sort of being a parameterization, morally speaking. So if you have this vector function, r of t is f of t comma g of t, well, it's literally the same formula, right? So I get that a vector function, it's if you think more in function-like language, you put in an input and you get an output, and the output happens to be a vector. But if you think of all of those outputs, so you get all these vectors collectively, but you treat those all as points, and then you imagine the picture drawn by all of those points together, you're asking for the length of that curve. Just as far as another way to write this integral here, I just did it for the 3D version, just to save on saying too many things, too many different ways. This is really so dx over dt, well, if the x formula is f of t, you're really talking about f prime, right? So this could have said x prime, it could say f prime because x is f, given by f of t. And then the point is what you see here inside the radical, including the radical itself, this is actually yesterday's derivative for a vector function, except, well, not just the derivative, it's actually the magnitude of the derivative. So it pieces all the things together. Okay, and this is the case because r prime of t itself is, so remember, r prime of t is you just put a prime on the f and then on the g here and then on the h. Therefore, its magnitude should just be, the square root of, well, whatever the magnitude formula says.